Hi, everyone. This is Deep Learning Classics and Trends. And today we're very honored to host Samuel Ainsworth to talk about Git Re-Basin. I love this title and I love this work. We received lots of nominations for this paper to be presented here. I don't know how many of them are submitted by Samuel himself. Not all of them. But yeah, so happy that this day has finally come. So Samuel, go ahead.
Well, thank you so much, Roseanne. It's truly an honor to be here and to be speaking with all of you. I promise I didn't pay anyone off. No self-nominations, but I'm really excited that folks in the community are as interested in this as I am. So thank you so much for having me. I'd like to do something perhaps a little bit unconventional and also perhaps a bit risky, and try a demo. So so I have here, oops, oh, look at that. I have here some a collab with some things. So could I actually get a volunteer from the audience?
Volunteer for what?
Nothing bad, I promise.
Sure, I can go ahead.
Okay. All right. What is your name?
Polina.
Okay. Polina, like that, or how?
It has an I, P-O-L-I-N-A. Yes.
Okay, like that. Okay, Polina, what is your favorite number?
Just a random number.
Just any number you'd like.
Okay, let's say 137.
137. Okay, wonderful. Thank you. Can I get another volunteer?
Now that people know what you're asking for.
Sure. I'll go for it.
Hi. All right, Robin.
Yeah.
Like that?
Yep.
Okay.
Seed 77, please.
77? Okay, you got it.
Thanks.
All right. And one more volunteer. Would anyone else like their name and shining lights here? Okay.
What's up? I can volunteer.
Okay, Robin. Is that right?
Yep, and 75.
75. Okay, you got it. So I think, let's see, I think we got all this. So I'm just, standard stuff with requirements, blah, 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 blah. And now we have, well, we'll let this run for a second. We have 3 random seeds. So so this is your card. Can everyone see your card? Okay. Now I'm going to train 3 models with these random seeds. So each model is going to have a different initialization and a different batch order according to each of these seeds, and they'll be trained completely independently. So I'll run that here, and we can kick this off. All right, so that's started. While that's cooking, let's go back to the real deal. So, all right, so yes, here we are, Git Re-Basin. First things first, I think deep learning loss landscapes are non-convex. I think we can all sort of agree on this. And if you're anything like me, when you think non-convex, this is the sort of picture that springs to mind. This is, kind of what you would see in your standard intro course or textbook or what have you. And what I'm going to try and argue for you today is not that this is an incorrect usage of the word non-convex, but that it's not quite the right mental model to have when we think about non-convexity in deep learning. And I'm actually going to advocate for a picture that looks more like this. So if I could put all of this project onto one slide, this would be the slide. So if there's, if there's one thing to look at, perhaps make it this one. So let's say that I train a model on some data sets, and I train into some model A, right, with parameters in weight space theta A over here. And let's say Roseanne independently trains her own model and a different, different universe, different computer, different everything, maybe even, different framework, whatever. But let's say same data set and, general architecture. And Roseanne trains to some model B with parameters theta B over here. And the the key point of our work is that if you just linearly interpolate between A and B, between our two models, that doesn't work, right? So I'm showing this is actually a real loss landscape for a model and a data set. And you can see here we have a high barrier, so to speak, in our landscape. And the entire story with Git Re-Basin is that we're going to introduce a bit of magic sauce to teleport this sort of model B over here to an equivalent model, so a functionally equivalent model. In other words, it's the same output for every input, but a different place in weight space, a permutation of the weights, what we're calling pi of theta b. And in this new location, suddenly you're in the same basin. So suddenly it becomes more or less convex. Now you might ask, okay, why should I care? What does this matter? And I'd say there's a few reasons. One is just sort of for science, right? It's kind of interesting to understand what things are happening geometrically in deep learning loss landscapes. I'd also argue that it's practically relevant today for all kinds of problems that you might care or not care about. For example, federated learning is a big issue for a lot of people. And in federated learning, the whole story is about how can we sort of independently train models and then merge them together down the road, right? Another case is maybe you don't care about federated learning, but you'd say, well, I just want to get state-of-the-art performance. I want to get the best possible performance. I want to get the most calibrated model. I want to get the best, X number model. Well, a lot of state-of-the-art numbers recently have come out of ensembles of models, sort of weight ensembles of multiple models. So if you look at like the model soups paper, there's many sort of results. Stochastic weight averaging is another work in this vein, right? Where if we just kind of average a bunch of things together, it does a lot better, right? And so there's a few different use cases where you might want this kind of averaging, and even if it's not perfect, it's getting you closer to some goal. Any questions on this so far?
I have a question on the definition of a basin. So that's just functionally similar neural networks with permuted weights, right?
That's right. And this is, I'm being intentionally a little bit vague on basin because I don't want to claim on a theoretical basis that it's perfectly convex. Because, mathematically, there's no proof of this, right? But I do want to claim that it looks convex. So, this is kind of banana shaped here, for example, which is you could say as well, that's, that's not quite, but it's fairly close.
Yeah.
Is there a straightforward concept or word or definition which is like convex but allows for curvature of the underlying dimensions?
That's a great question. So I am aware of, quasi-convexity, but I don't think that that's a perfectly tuned or relevant definition here as well. Like this particular 2D function would not be considered quasi-convex. That's a great question, and I would love if anyone has more answers or thoughts. I think that there's this kind of a gap here between the theory and practice of, pseudo-convexity. So yeah,
you could probably define it as like if you look at every contour line of the function, it's one line. It doesn't split into like multiple lines at any given level.
Oh, I see. Right. Right.
Connected. I guess every contour level is simply connected is probably sufficient.
Yeah, like all level sets are all kind of yeah. That's an interesting idea. Right.
Anyway, don't want to.
I think there might be an issue with that one. So just to chime in, because I've been thinking about this definition, and I know that nobody really defines it rigorously mathematically. If you have a Mexican hat type of potential, so imagine a hat and the rim of the hat. So you have a mountain in the middle, but the valley is circular. So I think there that would not be considered a loss base, like that would not be considered a single basin, even though this ring is connected.
Yeah, that's an interesting counterexample. Huh.
Is there any restriction to this on the number of layers?
There's no restriction, but my intuition is that more is not going to help you. I think it's like a lot of kind of model merging and robustness results where wider is good, deeper is bad, and everything else is TBD. Yeah. Yeah, it's a good question, but no real restrictions. Yeah.
Are the permutations happening within layers or they be across layers?
Good question. So this is actually going to be a great segue for a future a slide
Okay.
a few times down. I'll give you the TLDR right now, which is just that this is only within layer. But that is a restriction, and it may be a restriction that at some point we want to lift, right? I mean, you could imagine you can move features between layers. And in fact, one thing that I'm not going to present here today, but we do have in the paper is we sort of have a pen and paper kind of proof or counterexample that that this is not like a universal phenomenon. And even in all these models, we can embed a smaller model which does not obey linear mode connectivity for any permutation of weights. So really the magic sauce here is in SGD. SGD is sort of implicitly biased towards finding things that put similar features on similar layers. But that's like it's an interesting gotcha. And it's maybe also be relevant in all kinds of practical cases, like moving, if you have multi-head attention, maybe you want to move things between different heads, or, there's all kinds of, possible oddities. So.
Can I ask a quick clarifying question?
Sure.
You mentioned earlier, can you just kind of quickly, is the barrier just the blue area in between the two basins, or is it that line?
Great question. I'm going to use this actually as a good segue to, actually it'll be in like 3 slides. Is that okay?
It's your show, man. That's good.
Okay. I'll come back to you and hopefully I'll hopefully address your question. Exactly what that is. Yeah.
I have one question too. I'm sorry.
Sure.
So you're assuming when you're doing these interpolations that the weights are dense, correct?
That the weights are dense.
No, it's not a sparse model.
Yes, although maybe in a weird way, it actually is better if your activations are sparse. But that's interesting. This is sort of, I'm veering out of things that I know and into intuitions that I have.
Okay, the reason why I was asking it is, a direct interpolation between 2 sparse models would be somewhat nonsensical. So, right. But you still have the same phenomena that you were talking about with starting with random seeds and you get a convergence. So I was just wondering how that would fit into your general framework.
It's a good question, and no one knows. I think it would be a great experiment to run. Yeah.
Okay, thank you.
Yeah, absolutely. Alrighty, so just to provide, to set the stage here, the motivation for this work is there's a few weird things with deep learning, at least there were to me. So one is, why does SGD work in deep learning, but it's not an effective algorithm elsewhere? So before this, I was working on some policy learning stuff. And in that case, SGD works some of the time, and it works decently well on some problems, but on some problems, it just completely fails. Right. And this is weird because, like, coming from the machine learning world, I'm of the mind like, oh, well, just kind of, you throw more SGD at it and you go somewhere, hopefully. And so this is, this is weird. It seems like this is non-convex, but too easy somehow. It's acting convex. And then secondly, where are all the local minima, right? If I train my model, like, in that example before, and then Roseanne trained her model, I think people would be quite surprised if I got accuracy 85 and Roseanne's model got accuracy 60, or Roseanne's model got accuracy 97, right? Usually we run it twice and we get, maybe there's a little bit of noise in there, but it's basically doing the same thing. And secondly, why do they all have kind of the same training dynamics? And what I mean by this is, like, if we just look at a picture of, loss curves, right? I train my seed, someone else trains their seed. And even the loss curves over time, right? There's some noise or whatever, and maybe you fall off a plateau at one point in time, but it's basically the same curve with some noise. And that's kind of odd, right? That feels weird because that's not what we would expect in sort of a genuine, quote unquote, non-convex optimization problem. So this was sort of the background, the world in which, I was like, what is going on here? And I'm going to propose this one idea, which is, okay, maybe the permutation symmetries are to blame here, right? As I've alluded to up to this point. So if we have some hidden layer in our model, and I have unit 1 here recognizes cats, and unit 3 here recognizes dogs. Your model could have unit 1 recognizing dogs and unit 3 recognizing the 1 and the 3 are totally meaningless, right? It's completely arbitrary. As long as I sort of move these weights in the layers immediately before and after that unit, all the same, right? So, okay, idea, maybe we can sort of find some permutation of these things, and that accounts for some of this complexity. So I don't want to argue just that this is a phenomenon, but also that it's big. So if you look at a ResNet 50 and you count up the number of possible such permutation symmetries, it's 10 to the 55,109, right? Which is a big number, a really big number. That means that for every basin, somewhere there's a good basin with the best model, that basin is repeated in the geometry of the lost landscape 10 to the 55,109 times. That's a lot. For comparison, the number of atoms in the universe is currently upper bounded by an estimate of 10 to the 82, right? So we have, you just think about sphere packing all these sorts of things into the lost landscape somewhere. Where are they going? What are they doing? There's a lot of this out there. And I definitely also check out this paper by Rahim and others on sort of presenting this conjecture as well. All right, so the picture is going to look something like this. So I trained, some model A here to this orange spot in weight space, and let's say, Roseanne, for example, trains her model B over here. Roseanne's model, and the goal I'm going to have is I'm going to say, okay, I'm going to take Roseanne's model and I'm going to try and teleport it as close as I can towards my model. So for Roseanne's model, there's all these sort of replicated equivalent models in weight space. And the idea is I could pick this one, and if I linearly interpolate there, I get this kind of curve, right? So this is just walking in weight space on the x-axis and the loss on the y-axis. And I'm calling the barrier here the difference between the endpoints and the maximum, right? So this is coming from a wonderful paper from Jonathan Frankel and friends. And the idea is that, okay, maybe I can pick a better one in this sort of equivalence set, this, equivalence relation. And if I do that, I'm closer, and therefore I can get a much better barrier, and maybe even a convex barrier. Any questions on this bit? All right. So the main question here is, okay, yeah, this is great and all, but how do we find this pi, right? That's the million-dollar question here, because there's a lot to sort through, as we discussed. So in this paper, we present 3-ish methods, each sort of increasing sophistication or complexity, or however you'd like to think about it, each one building on the last. So the first thing that came to mind was, okay, well, let's just take the activations of my model, take the activations of your model, and let's just sort of try to match those activations, right? So if I have some unit in some layer and you have some unit in some layer and they have equivalent activation patterns, well, then they should be doing the same thing. So, okay, here's a easy algorithm. I'll take both of our models, run the entire data distribution. So I have some, all my data, run them through the models. And then for some layer, let's say layer 5, for example, I just create this matrix, which is sort of all the hidden units in my layer and all the data points. And then I do this for my model and I do this for your model. And then the question is, okay, I just want to find some association between these rows of our matrices such that we can sort of get them as close as possible. So mathematically, you can think of doing just standard ordinary least squares regression between the two things, but then constraining that onto the set of permutation matrices. And if you just sort of plug and chug some algebra, you get something that looks like this. And don't worry about the details here. The only interesting bit is that this is actually a very nice form. So this is a linear assignment problem. And linear assignment problems are nice because we have really fast algorithms for solving linear assignment problems, polynomial time, well-established. you can just go into SciPy and do it. There's nothing stopping you there. So that's idea one. Okay. Well, maybe you want to do something else. So here's idea two. Let's say we ignore the data distribution entirely. So just throw that out. Maybe if we think about our two models, if I look at my model and let's say I have, a convnet, let's say, for example, and in the first layer of my convnet, I have a filter that maybe is kind of looks like this. So I'm saying, okay, maybe that's like an edge detector that looks like this. And then I look in your model and I find, you also have a filter in some other place in your first layer that looks, maybe like that. I'm like, okay, well, that's actually pretty similar. So maybe this is the same sort of edge matching filter in our two models just by looking at the weights between the two models. So the idea here is going to be, okay, let's just minimize the distance and weight space between our two models. You can think about doing this as minimizing the L2, or you can think about it as maximizing the inner product. It turns out it's exactly equivalent in this scenario. And again, don't stress the math too much, just to notice that this looks like, so this is a linear assignment problem here, and this is a linear assignment problem here, but in the middle, we have this weird thing. This is something else, right? And you might wonder, what is that? Well, we prove in the paper, unfortunately, this is a different kind of thing. This is sort of we call it a bilinear, what do we call it? We used to call it a bilinear assignment problem, and we called it something else. Anyways, it's NP-hard. It's bad, right? Not only is it NP-hard, we proved that there's no polynomial time constant factor approximation scheme. It's just not something that you do, really. So, okay, that's a bummer. But I've never let. Oh yeah.
A question here. So, can you explain maybe in intuition for why this math does not work out the same as the previous one? Why argmax over pi, is this not just an n by n matrix for which Hungarian or Hopcroft-Karp would apply?
Good question. Yeah, what's the best way to think about this? I think the mess here is that if I'm doing, Hungarian or one of these kind of classic algorithms, I'm matching sort of, I have one thing here and one reference matrix here, and I'm trying to permute, the things here to matches here as closely as possible. And the problem here is that I'm trying to permute not just the rows, but also the rows and the columns. So doing both at the same time, it actually puts you into a land where it looks a lot like a quadratic assignment problem. So the proof actually is a reduction to QAP. And that's where it gets messy. You might be able to convert this into, like, you might be able to use Hungarian, for example, but you'd have to blow up your problem. You'd have to have some exponential blow up in the size of your problem, which I hadn't thought about until you mentioned it. And maybe, that's bad in theory, but maybe in practice it would work. It's not totally clear.
All right, yeah, thanks.
Yeah.
Yeah, I also find it hard to understand why weight matching is not exactly the same as activation matching, but just done with two different sets.
So that's, yes, perhaps this is, okay, so maybe I'll say it in a slightly different way, which is hopefully answers that question, which is a great question. So one really nice aspect of weight matching is that I do this for one layer, and I can do this for every layer independently, right? Because the activations at each layer are agnostic to whatever permutations you have below or above you. So I can actually sort of do this divide and conquer kind of thing where I just look at every layer independently, and I do these little, I can do sort of a linear assignment problem on each layer. I can run my Hungarian algorithm or whatever. But unfortunately, in the land over here, as long as you have more than two layers, you have to, if I permute layer 3, then that changes the assignment problem at layer 4 and layer 2, because I've actually changed, I've permuted one of the rows over here, but I have not permuted the rows in your reference model over here.
Wouldn't you do this layer by layer it's a feed-forward network, you have to first permute the first layer, second layer, etc., so that you don't have this consistency problem on account of the problem you just described.
Right. So that's actually the very first, as a fun historical note, that's the very first algorithm I implemented in this project, which is like start at layer 1. You have the first, your inputs are fixed, right? So I can just do that one, then go to layer 2, and then go to layer 3 and so forth. It turns out that we then tried this algorithm, which actually seems to work better. I mean, it's not that the other one's bad. It's just that you can also do this and it's a bit stronger as well. So just randomly pick layers out. If you just fix that layer, you look at that layer and you fix everything else, then that reduces to a linear assignment problem because it's just saying there's only one layer to look at. And then you sort of solve that one. And then you just kind of repeat this process to convergence. And it turns out that this does really well. Yeah, and one issue with just going forward is that it, at least my algorithm at the time, it only looked at the information from layers before you or under you when making the decision of how to permute, layer I. Whereas this algorithm actually, it looks at information above and below you. So if your downstream layers are expecting some feature that looks like X, you can match on that as well as sort of just the features you've seen so far in the model. Does that make sense? That was a bit of a roundabout way.
Yeah, that's a very interesting result. Interesting. Yeah, thanks.
Thank you. Yeah, and this is also when I talk about Git Re-Basin as an algorithm, this is usually the sort of headline one that I'm referring to. And finally, so we went from sort of activation matching assignment problems to now weight matching, using that as sort of the inner loop of your weight matching algorithm. Now let's try something else. Let's just learn it, right? We're all in deep learning, so we like to learn things. We just sort of throw more compute at it and see what happens. So here's an idea. Let's try to just learn what this is from our data. So here's a sort of optimization problem to consider. So I'm going to learn this theta tilde of B, right? So I'm going to move some model in weight space. This is actually a dense thing, so it has as many parameters as the original model. And then at every step, I'm going to project that theta tilde of B onto one of the actual permutations of theta B. And then I'll just look at the midpoint and sort of try to drive that midpoint loss down, right? And this projection operation, you can look at this and say, oh, that looks familiar. That's exactly what algorithm 2 does, right? So we can use algorithm 2 to implement algorithm 3. Now, okay, this is unfortunate because we all like, doing SGD, but this is not a differentiable operator. So what do? Well, we're just going to use sort of the straight through estimator trick. So the straight through estimator is a sort of a workforce algorithm in quantization in many of these areas. If you're not familiar, it's very simple. We're only going to do 2 things. So number 1, in the forward pass, we're going to do the projection. And number 2, in the backwards pass, we're not going to do the projection. And that's all there is to it. So in the forwards pass, we're getting actual, perfect projections onto this set of realizable values. So we're getting quality sort of, when we say the loss is X, that's a real loss. And then the backwards pass, we say, okay, actually we want dense updates. And that's what that looks like. All right, okay, and as a bonus, this is sort of appendix material, but I think it's fun, so I'll throw it in here. What if you want to merge more than 2 models at a time? So you can imagine that, merging 2 models is a bit restricting. Okay, so here's a simple algorithm. It's just, don't worry about details too much. The idea is I take my batch of models, I pluck one of them out, I average the rest of them, and then I try to make my plucked one look like the average as closely as possible. So I'm kind of constantly doing this. It's kind of inspired by sort of Berry Center mean approximation algorithms and different things in this sort of vein. Alrighty, now, okay, experiments. So let's see if we're done cooking, actually. I'll switch back over now to here. Oh, and it looks like we're good. So I'd like to try to do a live thing here. Let's see if this works. TBD. So
training, what data set was it?
So this is, I'm running on a free Colab GPU. So this is only an MLP MNIST. But hopefully I can at least convince you that it works on a simple case first. And then I'll have experiments on larger data sets in the paper and the slides. Okay. All right, so we have all of our, so Polina, Robin, and Pavan, we have your models. Here are your results. So let's see. Okay, looks good. Here's the train loss test, or train loss, train accuracy, and the same thing on test. Let's see. Oh, it looks like Pavan, you came out with the, you snuck out the win here in terms of the seed lottery. Okay, looks good. So now, let's just try interpolating between these models. So here's what that looks like. So in this case, I'm interpolating Polina to Rob's model. And you can see this is what the loss, the test loss looks like. And then Robin to Pavan and Polina to Pavan. Okay, great. So this is that barrier, right? This number here down to here, that's the barrier we're looking at. Okay, so now let's try running Git Re-Basin. So in particular, algorithm 2. This is all the code you need. So maybe 100 lines of code. That's all that's going on. And you can see kind of the general outline is here as well. So we're pulling a random thing out of the permutation of the layers. And then we're getting...
Can I ask you a question about these graphs with the naive manipulation? So it looks like in all cases, you're always doing better a little bit by moving away from the trained models in slightly. Right, because you always go down first, and then it shoots up. So do you have an interpretation for that?
That's a great question. I don't want to say anything definitively, but I'll give a hypothesis, which is that this is showing test loss, right? And I hypothesize that in the test loss landscape, you can kind of pick any random direction, and walking a little bit in that direction does a little bit of good for you for a little bit of time. That's a great question as to why that. Yeah,
that was my thought too, and maybe that's like a simple trick to squeeze a little bit more out of whatever solution you have.
Yeah, I think it might be. Yeah, it's really interesting why that phenomenon exists. It also may be that this is when I train, let's say Polina's model and Robin's model, they're going to have about equivalent sort of L2 norm of the weights. And it could be that just reducing and so if this is a linear interpolation, right? So we're sort of cutting through the sphere of, so the L2 norm is actually going to decrease slightly as we make this move. So it could be that just decreasing that norm just very slightly is a positive thing, which would align with, weight normalization and et cetera, et cetera.
Right.
Yeah, I see there's a hand raised, Pavan.
Yep. So I see that the highest loss is always at is usually at 0.5. Is that always the case, or is that is it just is that usually the case, or are there situations where the highest loss could be at 0.25 or 0.75?
Oh, you mean in terms of like the difference between here and here or something?
Yeah. So like if you see like at 0.5, that's the highest test loss for all three graphs.
Why is the ridge always exactly in the middle?
Yeah,
I think, well, I mean, you can make this argument kind of just by symmetry, right? There's no reason that your seed should be closer to something good or bad than anyone else's seed. So sort of just by symmetry, you should expect this to look roughly symmetric, right? Across lambda. Yeah.
Cool. Thank you.
Good question. Okay. So yeah, I won't belabor you with all the code, but it's short. There's not much going on here, and you could probably even code golf it down to be smaller. Okay, so great. Let's try running it and see what happens. So let's try to match. I think this is Polina and Robin's models. So you can see here it's running. So this is every layer it's pulling out, and this is the update. This is the improvement at that layer, right? And should just take a second, and we're done. So you can you don't have to believe me. You can believe Colab, but this is running on whatever the free thing is, so not a great GPU. But that was 14 seconds, and you can get this down lower as well. So let's do the rest of them as well. and then we can plot them. And here also, just while that's going, I'll show, I'm also printing out some differences in the metrics as we, before and after this move. So before, the L2 distance between these two models was 139, and then afterwards we got 120, so that's a decrease of 13%. But the inner product actually really shoots through the roof, so that you can see the inner product of these two models increases substantially. And this happens across the board.
And that L2 distance, that's literally just weight vector 1 minus weight vector 2. Okay.
Exactly. It just, yeah, flatten everything and then look at that distance. Yeah.
It's a little bit of a surprisingly small decrease given that you're optimizing for this, right?
Right. Yeah. Kind of curious, isn't it?
Do you see things like completely compatible rescalings and this doesn't take that into account? For example, if you multiply all of weight neuron 17's incoming weights by 2 and the outgoing weights by 0.5, nothing else changes.
Great question. We don't adjust for that. And that's one of these, that's another sort of class of, permutation symmetries that right now we're just sort of kind of, pretending it's not there. But it is there. Yeah, it is there. Now, one thing that's nice about that is that SGD is sort of, biased towards, keeping everything in expectation on the same scale. But that doesn't mean that it wouldn't be better to account for that, right? I'm just ignoring it, but someone should look at it. Someone should, yeah, check that. Yeah.
In higher dimensions, I think most things are far apart, so it's not really surprising that you only get a small L2 drop and a big inner product difference.
I see. So even if your move, yeah, I see. Yeah, that's a good point. All right, so now the grand reveal. So we saw what it was before. We saw the plots before matching. Now the plots after matching, suddenly we get convexity. So this is the result, I guess. This is the headline thing. Now, yeah, so you might also ask, what do they look like compared? I think it's just going to flatten everything out since the previous one was so high, but let's see what that does. Yeah, so you can see here, it's reducing the scale substantially, right? We're going from very not convex to convex, which is somewhat surprising. At least it was to me initially. So, okay. Next up, okay, so now I talked about this merging multiple models algorithm. Let's try running that. So this is same thing. We just pull one out of the batch, and then we sort of take the mean of all the other ones, and then we just do the weight matching between the two, right? So I weight match between the other models, and I weight match between myself, and I just keep doing that. So let's run that, and then I'll kick that off. And while that's cooking, I'll go back to the slides here. All right. Okay, so I'll just kind of run through experience. These are all things that are in the paper. So if you have any questions, there's plenty there to see. And also, of course, I'm happy to take questions here as well. So, okay, so here's the MLP MNIST. This is the experiments we're running right now. We ran all these methods. As you can see, straight through estimator and weight matching, it's kind of a little bit tricky. I don't know if you can see my zoom here on my screen, but one interesting thing here is that activation matching works, but it's not quite as good actually as weight matching. And this is interesting to me since weight matching just ignores the data distribution entirely, right? It's sort of handicapped in some sense, but somehow it's doing better. Here's a case where we have a CIFAR-10 and a intentionally underpowered MLP model, and you can see that it does not work as well, right? We actually have some barrier remaining, but this is a case where activation matching seems to do better, right? So suddenly activation matching is back in the running somehow. Again, I don't know if you can see my zoom quite as much, but yeah. And okay, next, CIFAR-10 is not out of reach. So let's try CIFAR-10, but with a properly powered model. So here's CIFAR-10 with a ResNet, and you can see we reach perfect connectivity. So essentially no barrier. And then finally, we have ImageNet. So in this case, I'm taking an off-the-shelf ResNet 50 model, and I'm not adjusting the width. So previously, I had to bump up the width here to get sort of the nice effects, and I'll talk about that in a minute. And here you can see we decrease. This is a 68% decrease in barrier, but it's not quite perfect, right? And so we hypothesized that as you increase this width, we could drive this properly down to 0. Next up, you might wonder, like, when does this show up? Is this true just across the board in training? Is this true at the end? What happens? It turns out that it's sort of an emergent property. So there's sort of this phase shift that occurs throughout training. In the beginning, it turns out to be very hard. And then over time, you sort of fall into this regime. And this sort of matches intuition about, like, in optimal transport, the quality of your solutions is depends on sort of the number of points you have, right? If I have vectors in some d-dimensional space and I have n vectors and I'm trying to match 3 vectors together, that's harder than matching 10,000 vectors together. I think the rate is something like big O n to the negative d or something like this. But it's just sort of intuitively, if you have more people to match against each other, there's more opportunities to do that. Sort of inlays to show exactly what that looks like, and then same thing with CIFAR. And also, I want to give a shout out here. Right after we put this out, another paper came out called I think it's above average initializations and how to find them, or something along these lines. I can also I'll share a link as well, since it's worth checking out. And they do something very interesting, which actually they managed to get this thing at initialization down to 0. And they do this by using information from the future of training, right? So if you pick my understanding of their work, I don't want to speak on their behalf, but is that if you can look ahead to what the permutation should be in the future, and then you backport that permutation into your initializations, you can get initializations that suddenly become sort of, you get convex, linear mode connectivity.
May I ask a question about the previous slide?
Absolutely.
So I was wondering, which methods did you apply there? So for this interpolation along training, which of the matching methods? Yeah.
This is weight matching. Yeah, that's a good question.
Okay, so this is all weight matching. And another question, what I'm struggling to understand, the interpolation at initialization. I would not expect to find an increase in the loss between 2 random initializations, because as I initialize, I expect I'm already starting pretty high. Now, this seems like it just reliably finds a higher point in loss between 2 initializations, meaning that somehow my initialization actually finds a more favorable spot on the loss landscape. Do you have an explanation for that?
Yes, that's a great question. I'll make 2 comments here. One is that I'm cheating a little bit. This is showing after 1 epoch of training. So
okay. That explains it.
Yeah, so there is that. Another aspect of this is that if you have 2 random, initialization schemes are actually very precise, and I don't think we give them enough credit all the time. In terms of picking the right norms for things and so on and so forth. And so if you actually mess up your permutation, or sorry, you mess up your initialization, and for example, you change the norms of units, weights and so forth, you can actually really mess things up, which is interesting. And I don't want to make any strong claims about that. But that is an interesting phenomenon as well. So that could be at play here. Yeah, that's a great question. Great question. All right. So I'll also say that there's, you might wonder, how does width play into this, right? As the width of my models changes, what does this look like? And there's some really interesting behavior here. So here's a VGG16 model. This is shown on CIFAR-10. You can see we tried different sort of weight or width multipliers on the number of filters in each conv layer, and as well for the fully connected layers. And it's a very clear trend here that, like, wider is better. And then here's a similar picture for the ResNet. Here you can see this is where we actually go all the way down to 0. And you really do have to, the 1x model is very skinny, so I guess bear that in mind, but I think this is like 256 filters per thing, maybe 512, but there's something categorically different going on in wider models. And what that is, I think, is a really interesting topic for sort of future exploration. There's an interesting question I think other people have posed to me in the past, and I don't have a great answer for yet. But it's like, is this because your optimization algorithms are easier, or because SGD is finding different solutions? I don't know. I think it might be some of both. But digging into that question would be a really interesting sort of topic. And I can pontificate on this a little bit if you'd like, but there's clearly some behavior here, and it would be nice to explore more about what that really is.
Do you think there's also?
I'm sorry. Go ahead.
Sam, do you think there's also a connection between whether a network is a ResNet or a non-ResNet? It seems to me that ResNets fundamentally have like far fewer degrees of possible permutation because the skip connections like have to keep things aligned block to block.
Good question. The ResNets caused me a bit of pain for exactly that reason.
Why though? Why?
Sorry?
Why do they cause you pain? Like you still have many layers within the blocks. You can still have arbitrary permutations, but across the blocks, it doesn't make sense.
Yeah, it caused me pain purely because the bookkeeping for what things you can permute and what things you're not allowed to permute becomes quite a bit more complicated.
For sure.
We have actually, I'm really happy to report that like my collaborator, Jonathan, who's absolutely fantastic, just in the last few days, he came up with a bit of PyTorch tracing code that you can just run your model through and it'll do it for you. So keep your eye out on that. That would have made my life a lot better. But yeah, but it somehow it seems to work just fine in terms of once you code it up right, it does the right thing. Yeah.
I have a real quick question about that.
Yeah.
Do you know the paper by Shimshak et al? Geometry. Sorry, let me look it up. Geometry of the loss landscape and over-parameterized neural networks, symmetries, and invariances. As far as I recall, it's a pretty mathy paper. And they have statements about the number of neurons, essentially the width of the neural network, and the connectivity, like the connected loss manifold. Do you know about this, and do you know any connections?
Interesting. Yeah, I've heard of this work, and I've looked at it in sort of the literature review, but I'm no expert in the work. I'd be curious to hear more about what their results and what the connections might be. Hopefully they're compatible. Fingers crossed.
We'll have two raised hands. I don't know who's the first, but either Robin or Polina, the ones with models being trained.
So where do you see this going, given that now you can merge multiple models together?
Oh, great question. Well, this is open for all of you to decide as well. I'm excited about a few things in terms of federated learning and sort of calibration of models, but also maybe we can get better optimizers out of this somehow. Maybe we can do like distributed training, where like right now training is a very serial process, right? I have many GPUs, but I need to sync them. Then I have to network sync them every single gradient step, generally speaking, right? Maybe we don't need to do that, right? Maybe I can just scale out. Like maybe I'm leaving the realm of things that we show in the paper, and I'm entering the realm of like things that I would like to be true in the future. But like maybe we can sort of just flatten this out, and like your large language model, you could just get like 10,000 GPUs, give each of them some of the data, and constantly just asynchronously, right? You don't have to take the network hits anymore, because you don't have to worry about being in the same data center even necessarily. And so maybe I can just throw weights around asynchronously, merge them together, and sort of make progress this way and make it faster. So that's something I'm excited about. But I'll also be curious for people in the audience there's certainly many other things, right? I don't limit yourself to my own creativity. Go out and explore and so forth. So, yeah.
I'd be curious to see what your loss barrier looks like if instead of doing a linear interpolation across a space, you did a rotation, like a slurp, then a lerp.
Good question. We actually tried this, and it does work a little bit better as far as I could tell, but it wasn't enough of a difference that I felt comfortable sort of deviating from the existing literature. So if you go to implement this sort of in a more practical or whatever sense, that may be worth something looking into. Yeah, absolutely. It's a great question.
I had a question. Sorry.
Can we respect the raised hands? Because Polina and Robin's hands have raised for a while.
Oh, sure.
Yeah, sorry. I was wondering whether you checked. So like you have a model and then you have two independently trained models, and then for like the model B, you can find a permutation such that the permuted model is close to the model A, and those are close in terms of like weight space. But have you checked whether the original model B and the permuted model B are functionally similar, as in, do they have sort of high agreement on held out data? Like, do they represent sort of similar functions, or does the model B become closer maybe to the model A as it gets in terms of the function space, as it gets closer to model A in the weight space, if that makes sense?
Right, right. So what I can say here is that it is exactly equivalent to your original model B. So on all inputs existing and future, it'll be exactly the same thing. And if it's not, that's a bug. So this is something that we tested as well, where we just, anytime we define a sort of the permutation symmetries of a model, we just apply random permutations and double check that on any data it's equivalent. Because that's exactly, we want to maintain this invariant, you know, in code and in theory.
Okay, yeah, thank you.
Robin, I think you're the next.
Hey, just briefly, I have a very basic question. Thanks for the talk. Are the different models always trained on the exact same data sets, the exact same data points? And when could you maybe break that?
Great question. That is my next slide. So I'll talk about that right now. Maybe I'll take, it looks like we have one more hand up, Manav, and then I'll get right to this slide.
Yeah, sure. So my question was very similar to Robin, as in the 3 different models which you are training for the MNIST. The seed which you're providing, you stated that it helps in changing the order of the mini batches and the initial weight initialization, but they're still training on the same 60,000 data samples of the MNIST, for example. So I wasn't able to see the difference in the data set or the different models over there.
Yes, and actually I have that experiment as well. So I can show you both of these now. So this is an experiment, I'll make this fast since I know that we're running short on time. This is an experiment where we took CIFAR-100. We split the data set up into 2 disjoint data sets. Each one is biased. So the idea being we want to explore bias in models. So data set A is biased towards labels like 0 to 49, and data set B is biased towards labels 50 to 99. And now we sort of try what happens if we train independently and then merge them. And we get this nice behavior that actually our merged model outperforms both of the input models in terms of the loss and in terms of other metrics I'll present in a second. We're not going to beat ensembling that has twice as many parameters, right? So that's out of the question. And we're not going to beat full data training since that's cheating, right? But we're actually outperforming both of our input models. And not only that, but I'll show you this. This is the same experiment, but now we're going to look at the calibration of our models. So on the x-axis, I'm showing the predicted probability coming out of the model. And on the y-axis, I'm showing the true probability of the data being a certain class. So for example, if your model predicts that it's a cow with probability 10%, then 10% of the time that you make that prediction, it should actually be a cow, right? And so this is the results that we get. So model A and model B here are shown in blue and orange, respectively. And you can see that we actually have quite poor performance. So ideal performance is this exact straight line, right? And we get this sort of very weird performance here. If we merge them naively, we get even worse calibration. But if we do our Git Re-Basin matching, we get nearly perfect calibration, even though each of the input models is biased. So we can actually sort of de-bias in some sense the probability estimates. And then on test, the result is not quite as strong, but it is still, the effect is still there as well. And then I'll hop back to, I know we have one more thing here, just to see how this looks. So we're done merging these models. That took 1 minute. And let's see what it does. So here you can see, okay, test loss 0.15, 0.15, 0.2 for all of our input models. After we merge them, we get a test loss of only 0.08. So we've actually decreased the test loss by merging just these three models by 44%, right? Which is a nice improvement. I'll also take that to lead into the rest of these slides. So I know there's a question, I think Manav asked, what if you merge models that don't see the same data necessarily, but they're not biased? So here's an example. We trained 32 models on MNIST, each one seeing some random subset, some random 50% of the training data. So that's all these orange curves here. And then we merge all 32 of those together. And what do we get? We actually get something with much better calibration out. That's the green line here. And a similar story on test. So I know we're running short on time, so I'll try to wrap up here quickly. I'll just say that as terms of some final thoughts, it looks as though loss landscapes in certain cases seem to contain only a single basin. Modulo permutation symmetries and some other details. I don't want to claim that this is true in general. It's certainly not. As we show in the paper, there are counterexamples to this, pen and paper sort of cases you can come up with. And a great question, I think, for the future is, can we categorize failure modes, right? They exist, they're out there. Can you find them? Are they out? What do they look like? Where does this happen? How does it work? I think that would be nice to aid our understanding. Number two is that we can, on a practical note, we can do this merging. So you can take your model, I can take my model, and we can merge them together. I'm curious to hear sort of what the future will look like in terms of maybe this is a useful thing, maybe it's not. Hopefully something comes out of it. And finally, we can actually get better sort of numbers out of doing this. So if we merge these multiple models, we can get better calibration results. And maybe this is an avenue for, I don't want to claim this as truth or anything. This is still up in the air. But one thing that I'm excited about, I'll say, is the prospect of using this for improved sort of, model training. If you have the compute for it, train multiple models and see if you can merge for better results. So with that, I'd like to say, these are some comments we can come back to in a second, but I'd like to say thank you to all my wonderful collaborators. And thank you to all of you for coming here and asking so many wonderful questions and being willing participants in my demo. And so thank you so much. Thank you for having me. It's been an honor. So.
Thank you, Samuel. Can you stay a bit longer or do you have to go?
Absolutely, yeah.
Okay. So we can do open questions now. I got confused why there's only one basin, because it looks like if you can permute B to be in A's basin, you can also permute A to be in B's basin. To start with, that would that already be two basins that work?
Yes. So my claim here is that there's only a single basin modulo these symmetries. So in reality, there are many basins, but perhaps they're all just the same thing being sort of reflected throughout the space because we can do this teleportation between them.
See.
Yeah, that's a good question. Yeah.
Okay, we're open for questions. If anyone wants to speak up.
Could you go back to that slide that you just skipped over, which is your future thoughts? Yeah, there we go.
Yeah, so I just threw a smattering of different ideas here, kind of for open-ended discussion with everyone on things that I think are sort of open questions remaining and possible future work. And this is, feel free to totally tune out if none of this is, you feel is relevant or sometimes people, questions or, different things, but these are the things that I think are interesting in the future. So I'm personally excited about it, so.
I have a question about the role of SGD. So here, one of the open questions that you ask, why is SGD implicitly biased? So what's the difference with Atom optimizer? I know that there was some back and forth on Twitter as well with Stan, so maybe you can clarify like the resolution of this.
Yeah, it's a great question. So Atom works as well. So in particular, the collab we just ran was with Atom. in the CIFAR results, the ResNet results, the VGG results, those are all with SGD with momentum, and sort of a very standard kind of, you know, computer vision, like linear rate warm up and then cosine decay. Yeah, I don't know. So Stan came up with an interesting case where it looks like you swap Atom out for SGD and something doesn't work. And I'm not sure what's is going on in his code necessarily, but it would be interesting to learn more. It does seem like this maybe fall into one of these categories of things that either works or doesn't work, or maybe it has something to do with the width. You need a larger width when using Atom versus SGD or vice versa. I don't know. He also, I noticed that in his thread he mentioned that there seems to be some sort of effect with the learning rate. So maybe that's an interesting avenue for future ablations. The honest answer is I can't say. We haven't done enough experiments yet. We don't have enough ablations to really dig deep into this. But I can say that, like, you know, we present results. The paper has results both on SGD and on Atom and different models, and we're using quite standard off-the-shelf stuff. So there's no we didn't have to play with that in order to get where we got. So it was a surprise to hear that, like, there's cases where, you know, you can mess with it and so forth. So.
Okay, cool. So it's really not a particular property of SGD, but extends to other related algorithms.
Yes, that's the current, the current belief. And it would be interesting to dig more into that. You know, I think there's more to be said there. The story may not be finished. Who knows? Who knows?
Brian?
Oh, yeah, I had a question about whether, since the loss function doesn't necessarily mean that the two models are functionally equivalent, could you now create a situation where, while you have them in the same basin, you can create like an example through some sort of adversarial search that reestablishes like a wall between the two examples to see what those examples would look like?
Okay, so I start with, like, I have two models in the same basin.
All right.
And then maybe I do something to try to create a barrier.
Yeah, to create, like, you could search for barriers now, right? Like by generating samples that, when incorporated in the loss, would have a barrier between the two.
Oh, I see. Well, yeah, you can always just randomly permute one of them to create a barrier. But I guess maybe you're asking, like,
in the input space, like, can you create a barrier that's an artificial input example?
And that's an interesting question. Yeah, like, if you're willing to deviate from your data distribution, can you find some way? I don't know. That's a great question. I think just in terms of sort of you know, a Lipschitz kind of argument, you can say, like, well, if I'm close by in weight space, then my function should be sort of Lipschitz similar somehow. Then maybe that's hard, but I don't know. It'd be interesting to see. Like, yeah, maybe there's something to be said there. Like, because maybe it is all in the data distribution. I don't know. Who's
right? Because then, like, you can also, like, potentially argue what is functionally different about these models through some sort of optimization search.
I see. Yeah. It'd be interesting. Also, it sounds similar to sort of, you know, Jason has this convergent learning paper, which is wonderful as well, and touches on this. Like, it'd be interesting to sort of try to connect them through this lens of, yeah.
Hi, can you show me the collab screen?
The collab screen? Yeah.
Yeah.
Let's go here. Yeah.
So even though the test loss is now low, we are seeing that the test accuracy also decreased, right?
Yes. So the test accuracy does, decrease slightly.
So does this mean the confidence is increasing, the interpolated model's confidence is increasing, and not necessarily its performance?
So if I understand the question, it's like, perhaps what's going on here is just that we're decreasing confidence somehow. Is that correct, or?
Like when loss decreases and it doesn't mean an increase in test accuracy, we usually say, like, sometimes we see that the confidence is increasing and not necessarily the classification performance.
I see. Right. Yeah. So like what's going on here?
Do you notice this often, or is it just a random?
Yeah, one thing I will say is that it does seem as though merging has a slight negative effect on accuracy, but a very positive effect on your test loss and your calibration. Now, yeah, why that is kind of an interesting question. I'm not entirely sure. I don't have a solid, definite answer for this. But I do think as a community, we are perhaps a little bit over-focused on accuracy as a metric. For example, my employer at the moment is sort of in the autonomous vehicle space, and you can imagine that when you are deploying models on an autonomous vehicle, you might care more about having well-calibrated and robust estimates of probabilities than having top-line accuracy of like top one results. But yeah, exactly why this is happening is a great question. I'm not entirely sure. So would be fun to like look into that.
Yeah, thanks.
Yeah.
Yeah, hi. So yeah, thanks for the great talk. So I was just wondering, have you tried maybe merging models of two different tasks? So here all the models have been on same set of classification levels probably. So what happens if we have two similar architecture models, but they are solving two different tasks?
Yeah, that's an interesting question. I don't have an answer for this. I mean, we do have this sort of, biased data set situation, but maybe if you just went to like, data set A has these labels, but none of those labels, and data set B has those labels, but none of these labels, what happens? It's a good question. I don't know. I mean, I imagine it'll do something, like it's hard to be worse than naive. But it would be an interesting sort of topic for like comparing this with other sort of, continual learning ideas. I'm not entirely sure.
Yeah, right. Thanks.
Hey, I had a question regarding the calibration. So you show that the merged model has better calibration compared to the like model A and model B. Do you also see corresponding, or have you tried corresponding out of distribution detection performance? So does the merged model have better out of distribution?
This is not something that we've explored yet. I don't know. Yeah, it'd be interesting to try, doing some kind of, truly like genuinely out of distribution thing. So you pick some data set that's like totally different. I don't know. It's a good question.
I have a hand wavy explanation of the width thing. Why does increasing width help with the merging?
Yes.
I think if we don't have enough width, we don't have enough feature extractors. So maybe when you try to merge two models with lower width, they're actually building up different feature vectors. There's not a perfect matching. For example, if you're trying to detect a head, one model maybe figure out we should detect ears, eyes, and nose. If they only have 3 features to work with, the other thought hair or something, then there's not a matching. But if you allow them to have 100 features, at some point they're going to develop all the relevant features. Just hand wavy.
I think that's exactly. I mean, okay, I'm veering into things that I'm thinking but don't have results for. I think that's exactly right, or at least it's exactly what I believe as well. There's an interesting blog post / paper out of Anthropic recently about this topic, arguing something similar, that I think if you have a wide enough model, like let's say just as many units as you want, you can kind of perfectly put one feature on each unit however you like. And when we're training these skinny models, I think maybe what's happening is, you can kind of Johnson-Lindenstrauss your sort of activations down sort of, and you still get decent performance in top line metrics. But what's happening inside the model is different, right? And then you need rotations, and you can't put rotations through element-wise activations, and then da 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 da. So, but yeah, I think you are so. I think that's a very prescient.
Yeah, and philosophically,
observation. Yeah.
We have less degrees of freedom to develop anything. We end up with a more diverse set of things, but if we have large enough degrees of dimension to work with, maybe we eventually are very much alike. Just a philosophical comment.
Yeah, absolutely.
Manaf, did you just raise your hand, or that's an old hand?
Thanks for the talk, Samuel. I just wanted to quickly check if the biased dataset code is up on the Git repo as of now, because I see like the seed code is there, and like when I tried supplying two biased datasets over there, two biased trained models, I couldn't reproduce the results. I just wanted to check.
Oh, really? Okay. Yeah, feel free to send me like a GitHub issue or something, and we can work through it. There should be everything uploaded to the GitHub, but if not, we should double check that. Were you running from the scripts that are the training scripts that are also in the repo, or were you training elsewhere?
Yeah, I tried to use the PyTorch version of it, so probably.
Okay. Yeah, okay. I don't have any PyTorch code in the repo, at least not yet. So the PyTorch version is written by someone else, and I don't know totally what's going on there, but we can debug at some point. If you run the JAX version, that's exactly the code that. Also, if you go, there's the weights and biases sort of project for this is public, so you can actually see exactly what experiments produce which plots, and all the hyperparameters and so forth as well. So that's also open source, and the model checkpoints are open source as well, so you can download them. But yeah, I'd be happy to like dig into this over email or GitHub issues or something. Because
sure.
Yeah,
sure. Thank you.
Yeah.
Okay, maybe one final question. If anyone wants to ask.
How did you get those pets in your little collab?
Oh,
That's a Google thing, right?
I at some point, like a few years ago, I was playing around with the settings and I put all this up, and then I totally forgot until today. And I think it's a presentation.
I thought it's a Google theme for Halloween or something. It's always like this for you?
This is definitely, yeah, this is some kind of Halloween something for sure. Let me find editor. Yeah, wait, how did I do this nonsense? That's a good question. Oh, here it is. There's corgi mode, kitty mode, and crab mode. Oh, and you can change. Okay, let's see what if I enable all of them. What does that do? This is the moment we just.
Oh my God.
Now we have crabs too. I see. So I guess that's the answer. You go up to settings and then go to miscellaneous, and then they have these modes. I don't know if it's professional to have all this on my talks, but I forgot to turn it off. So yeah.
I consider it professional. Thank you. Appreciate it.
Thank you.
Professional for DLCT at least. Cool. Oh, look at that kitty, purple. All right. Thank you all. This was really fun. You're such a great talk giver. So good to have you, Samuel.
Well, thank you all so much, and thank Roseanne for organizing and inviting me, and I really appreciate it. It's been a lot of fun. So thank you all for the great questions as well. It's been good.
Cool. Thanks. Have a great weekend, everyone.
All right. Thanks, y'all.
Bye.